passing through the point f minus 1. Okay, so therefore now you can using the point slope formula as I just given, so which is y minus y, the point y, so minus 1, multiply the slope m, x minus 1. Okay, and then you simplify, you get y, you have a plus 1, you can actually move it back to 2x plus 1 will be your simplified equations of tangent. So therefore, this equation tangent is simply as y minus 2x plus 1. Okay? So it's quite standard now, finding. You can, one certainly is not important, you can find any other points for the functions. Okay, so then reduce the tangents becomes just need to find derivatives. Okay, so now this is about the tangent. This is not the Newton idea, the objective, the goal to invent the calculus. He actually looking at the physics problem, looking at the velocity. So okay, so now this is the Friday lecture. Okay. Okay, so well, what is this about? The derivative is a fairly basic object of a function, and the application, there's a different various applications. So first, I understand this is the slope of the tangent, right? The meaning of the derivatives. Now I actually write, also you know that this is an instantaneous rate of change. Okay, now this time we talk about the derivatives, in fact, is a velocity. If my function is a displacement function, okay? If my function is a velocity function, the derivative becomes an acceleration. So they solve a fairly basic problem in physics. Okay? Well, for example, so I throw a rock into the air, going up and fall down, and try to measure the height. So this is my displacement, and then you can compute the velocity. Okay? And then you plot. So this is my displacement graph. Okay? Positions you actually measure from the ground. So increasing because you're going to the top and then decreasing. Okay? So this is why you have a maximum point. You have forward up, you have the highest point and decrease, and hit up to 0, you soon have the negative there, because there's no negative distance. You cannot under the ground. Okay, so from 0 to 0, so this is hitting the ground. The ground again. Right? So this is a very simple model of physics of motion flowing up. Okay? But I want to study this more. I want to say, for example, finding the speed of velocity. Before the calculus, just like the tangent, we can consider average velocity. So this is the change in position. This is the time difference. Then this will be a secant line. When you do the experiment, what you can do is say, for example, for time one I can measure, and then for another time I can measure another height. Okay? So this is how I can do for my experiment. You have a different time, so you can compute the average velocity. So this will be rise and run. Will be F. You have different time, so different displacement. Okay, you have different time t1, t2. Okay, so that will be the change in the position or displacement. So you're moving like the car. So at a time, okay? So what this is actually telling you, this is average velocity. So imagine that, say, not following a car, a rock. You're driving a car, you can from time 0 you measure the distance, and after another time you measure the distance of the car, and that is the average velocity. Okay? If you have experience driving a car, the average velocity, we change the velocity all the time. Whenever you press the gas pedal, you actually change your velocity. The velocity means you keep the same speed. Okay? So this is the average velocity. Average velocity is actually not describing the actual situation. Very precise. Okay? What you actually need is actually called the instantaneous. That means is you consider time change in at a moment, instantaneous change. So in other words, when you change it, you press a gas pedal. When you press, it's just a very short moment. Okay? Then that will be the instantaneous. Well, the same idea, when you take the limits, when delta t tends to zeros, then you'll have a tangent line. Okay? So therefore, now, instead of the average velocity, now you have, after the limits, you have an instantaneous velocity. This will be the same object, because from the graph you have this, it's the slope of the tangent line. Okay? In fact, if you want, if your curve is a displacement functions, the instantaneous velocity, that is the usual velocity we mean, is the slope of a tangent. Okay? So you should ask, why does this make sense? And we only know one point, so how to get the tangent, how to get the slope. So this is precisely we asked before. Because this is actually, I put a delayed this slide. So we already discussed how to take the limits. So for samples like this, we actually try, why we take the limits, or we actually, one way to do it, we can do some experiment, compute some limits here. Say for example, I want to consider this time. So I'm choosing different time. This is my 5, and I'm choosing the time very close to 5. So after very close to 5, so you're approaching the limits. Okay? For example, this is the calculations the graph is about. So I'm starting from 1, 9, and the point I want to find is 2, 5. Okay? Cooling down, the system is cooling down, please wait approximately 60 seconds. So the point is 5:25. Okay, so let me say, I actually, so the idea is I want to find the point and compute the numbers, see what happened. So I'm starting from a very far point. Actually, the t is 1. My target is actually t equals 5. But then you have a time difference and you have also the position difference. You can compute. So the distance is 25/9 and 5 minus 1. Okay, so you have 16/4. So you get 4 feet per second. Okay, so this is an average velocity. For the time period is from t1 to t5. Okay, then you can do a similar calculation by choosing t equals 4. So 4 close to 1, closer. And you compute the 424, and you have another one number given 5. And then you keep choosing as time which is closer to 1. So now, and then 3, and then 2. Okay, and then you have 5, 7, etc. So you can see the tendency in 4, 5, 6, 7. It's keep increasing. Okay, and then you choose a very close to 1, say 1.001 here. Okay, now this only gives you the idea how the tendency of the function. This is not the way to compute the limits. And when you compute, you get 799. Okay, if you're not satisfied with it, you see that it's very close to 8. You can choose 1.0001 and you get closer to 8. So you will expect from the data the instantaneous velocity at 1, in fact, should be 8. Okay, but this is just a numerical data suggests it's approximation. Okay. For the case, so let me say, give you the function. So function is y equal to 10t minus t squared. Okay. The 8 is actually coming from, now you find this is my f of t. The f of t1 will be the limit, and that will be equal to ft plus 1, f1 over t tends to 0. Okay, the t is the delta t. Okay, then you will actually get 8. You compute, you follow the limit, you will get 8. So that is what exactly what the meanings. Okay. So this slide, I think I go through last time, so I already have the complete note, so let me skip this slide. It's the same thing for the tangent. More interesting is, because it is most of the major is actually business, so let me talk about some application in the business. Now, of course, you don't study velocity a lot or tangent a lot. But the key concept, the rate of change, is all happen to all subjects like business. You have some function you want to study. You have demand functions, profit functions, cost function you want to study, right? Now, for example, the cost. The cost is a function of x, how many x you produce, and then come to the total of cost. If you want to study this cost function, you can still also consider rate of change. If I change x, okay, if I produce my quantity from 5 to 10, so I have different costs. What is the rate of change of the cost in respect to x? I still want that. Okay? So for example, a manufacturer has determined, say, this is my demand function. Okay? The last example